what we are going to try to talk about today is the challenge that I wanted to combine this headless JUCE audio library, so headless without a UI, and consume that library from a Xamarin CocosSharp game application, or game app, a mobile app. So Xamarin, I don't know if how many people are familiar with Xamarin. Not that many. So Xamarin is a tool set for doing development on mobile platforms, and it's also cross-platform like JUCE, but you typically write your code in C#. So it's more geared towards people from the Microsoft background, like myself, for instance. Before you say writing in C# for audio applications, that's preposterous. Well, there are actual people I think that like doing that. I know this because I'm one of them. And to make it a little bit more spicy even, I did not want to use, didn't want to build a plain Xamarin UI, but instead use a gaming framework to build the UI. And in the Xamarin ecosystem, the go-to gaming framework is called CocosSharp. And CocosSharp is Xamarin's port of the quite popular Cocos 2D framework that you might have heard of which you have also C++ versions and Objective-C versions. Now, you're not, of course, obliged to use CocosSharp gaming framework to do a UI in Xamarin. You can also build more classic-looking mobile UIs, which are more native-looking. I will give you a brief glimpse of that at the end of the presentation as well. Okay, I hope this is readable because the resolution is a little bit low. So this talk is basically split into two parts. The first part is building that JUCE-based audio library, which is entirely C++, of course. And the second part of the talk is about putting that Xamarin UI on top of that library. Now, the design of that audio library, in this case for the sample, so this is not for the real project, but the real project has a similar structure. In this talk, I described the sample, which is basically built around a JUCE tone generator audio source that you plug into an audio source player and hook up to an audio device manager in order to sound a test tone. So congratulations, this is I think the third sine wave demo of today that you will be confronted with. So these are JUCE classes here. Then I have this simple main entry point class, CocosJuice main I've called it, which is basically a wrapper around this, which keeps the references to the JUCE objects and does the initialization. And it has a number of methods that, first of all, implement the business logic, let's say, where you start, stop, test, tone, and choose the frequency. And also some more lifecycle management methods like pause application, resume application, cleanup at the end, and stuff like that. Now, this is all C++. Unfortunately, we cannot stop with that because we cannot, in Xamarin at least, we cannot call directly C++ objects from C#. So what we need to do is put a little layer on top in the form of C export functions, which is just plain C. And that's really simple because these are just static methods that more or less map one-to-one to the methods on our JUCE class, on our custom JUCE class. Right. So every JUCE project starts with the introducer, as you all know. So also where we are building our libraries. Here are some introducer settings that are different from the default settings. I'm not going to discuss them all, we don't have time for that. But the important thing to remember is that you need, is that there is a difference between iOS and Android here, in the sense that for iOS, you are required to produce a static library, a .a, whereas for Android, you have to produce a dynamic library, a .so, or a shared library. This is because Apple does not allow you, to my knowledge, to deploy your own shared libraries. Technically, the platform can handle it, but I don't think you can deploy them. Whereas with Android, it should be a dynamic library because that's a limitation of Xamarin. To link with Android libraries, they require that it's a dynamic link library. Now, this is only a minor annoyance, I think, because the annoyance is that you need two juicer projects, but you can share all the C++ code by including it in both projects. So you need to write the code only once. Some stuff to pay attention to. It's not really readable, but I'll explain it. So the first thing is these C export functions. In itself, they are quite simple, but very important on iOS, they need to have a proper export attribute visibility default. If you don't do this, you will grow a few gray hairs, like I did in the process, so I can spare you that already. For Android, you don't really need any extra attributes, so that's trivial. And for Windows, which I'm not discussing here, but you cannot do all this stuff also with the Windows GUI front end, then you would need a third kind of export attribute in your C code. Okay, another thing that's important is that you should at some point initialize your JUCE library. And on iOS, that's quite straightforward. There, JUCE provides a initialization function, initialize JUCE _ GUI, which suggests that you initialize a GUI, but you are not forced, of course, to implement the GUI in your library. So this also initializes the rest of the JUCE system, including the audio system. We call this typically in the constructor of our main entry point class that's in our library, so that we have a kind of lazy initialization here. On Android, it's a little bit more involved. So on Android, first of all, what you need to remember is that what the introducer will do when you generate your Android library, it will generate also a .java class for you, a Java source code class, which implements Java C++ interop, and which helps the JUCE C++ code to talk to the Android APIs, and which also initializes the JUCE Android system. Now, you're not doing anything with this on the C++ side right now yet, but this will be important on the Xamarin side, on the client side later. Another thing you need to do, as far as I know, is to prevent one additional implementation of a JUCE application class, only for Android here. And this can be a dummy class. It doesn't really play a big role. It just has to be there and callable in order to make the linkage of the dynamic library succeed. Okay, once we have written the code, then we need to build them, to compile them and link them in the case of the Android shared library. This is just a regular way of doing it. So on iOS, you build with Xcode. I used Xcode 6.4 for my sample. And on iOS, you will then end up with two static libraries, one for the simulator and one for the iOS device. On Android, you build with the combination of the SDK and the NDK, the native software development kit, also in the standard way that JUCE normally requires you to do. And the output there is 3 dynamic link libraries, one for each processor architecture, so ARM v7, and x86. By the way, all these libraries are of release quality. You can also make debug versions, but I tend to do the debugging first in another context, and then only when they're ready, then I make release versions, and only then I start building UI on top of it. So, at this point, we have done all the C++ work. We have created our static libraries for iOS or dynamic libraries for Android. And now we move on to the UI side, which is the C# side. Before doing that, I'll give you a quick demo of the functionality. Hopefully it will work. Just for iOS to save time. So here is the UI of the test tone generator. It's really simple. You have just an on-off switch, and you have a rotary dial to select the frequency. So if I click on this, I should hear the test tone, and then I can vary the frequency. What you see here is not a native-looking UI. What you see here is the CocosSharp way of doing a UI. And what you actually are seeing here is that I've used CocosSharp objects like a sprite. A sprite is a special class that's meant to be used to represent game characters that move about in your game and that are animated and have to be very fast. Now in this case, I use a sprite to do an animated rotary button. So I do not have to do a game. I can just use the game infrastructure to do animated UIs. Okay, back to the slides. All this code, by the way, is available on GitHub. I'll show you the link afterwards. I cannot show, due to time constraints, all the code, of course. But I can tell you what, in general, what the structure is of the UI side. So when you download the source code, you will find a solution called CocosJuice app.sln. And when you open that, you can open that either in Xamarin Studio or in Visual Studio if you have the Xamarin business license. Then you will see 3 projects in there. One project for Android, one for iOS, and one shared project. The Android and iOS project typically contain just a little bit of startup code that's necessary to bootstrap stuff, whereas the shared project contains the bulk of the UI coded against the CocosSharp APIs, which are also naturally cross-platform. Now, as you remember, we have these JUCE audio libraries that we have to consume from our C# UI. So how are we going to do that? It's really unclear. Can we maybe change the resolution, or is it? No?
Change it in the monitors. Pushing system preferences. Should I do it? And then monitor displays. Scale. And try a higher one. Yeah,
This
try
one?
that one, yes. I don't think it does anything higher yet. Try that. Just a second. Yay. Confirm. Yeah.
Let's see if it
It's
does
a bit
anything.
scaled then, though.
Ah.
Yeah.
Oh, not that much better. Okay, I'll try to read aloud. Yeah, sorry. So what you have here is at the bottom side, you have our C exports that we already talked about. These are already in your libraries, in your JUCE libraries. And then we have to provide a C# interop class that talks to these C exports. And this is really a very simple class which has one method, C# method for each C method. And yeah, you cannot really read it, but you have just a simple static method definition with no body. And then you have here an attribute that says, okay, this is the C name of this method, and this is the library where you find it in. And then you have optionally some other attributes in order to fine-tune the marshalling of the input-output parameters of these methods if needed. So basically, this here is just a C# interop class for the C library. And then you will call these C# methods from your C# code. So you will call them typically from the Android iOS startup classes in order to do typically the lifecycle events of your application, like pause and resume. And from the game class called intro layer here, that starts and stops the test tone in this case. I just said that we need to call this C# interop class from our iOS startup code. So in iOS, you have an app delegate class. It's sort of the entry point of your mobile application. And there you have convenient overrides like did enter background, will enter foreground, in which you can call the similar lifecycle events on your API. And in your API, you do what you wish, like suspending audio or resuming audio, for instance. On Android, again, it's a little bit more involved. What we have on Android is that, well, to start with, we have a similar thing as with iOS. We have a kind of initial startup class, which is called a launch activity in Android. And in that launch activity, I can call the yellow, can do the yellow calls here, which is similar as in the iOS call, where you do the lifecycle calls of your API. Now, but there's an additional step on Android that is needed. Now remember that I said that in the C++, generated C++ code by the introducer, you found also this Java class that was generated by the introducer. And normally this Java class is supposed to become the launch activity of your Android mobile application. And when a normal JUCE application, that's quite convenient. You can just let it do its thing. But here we face a problem because here we already have launch activity and it needs to be of type Android game activity. And we cannot find a way around that. So what to do? Now, the workaround I found, and it's admittedly a bit of a hack, but it appears to work, at least for audio, is that from my own startup activity, I manually instantiate the JUCE-provided activity and call the initialization method in there and several of the lifecycle methods. Obviously, that's not an ideal way of doing it. So in an ideal world, the JUCE team would perhaps consider providing another way of initializing the Android subsystem in a mobile app without requiring you to substitute your own launch activity. So a few more words about this Java activity class that was provided by the introducer. In principle, you can just take that code as is. You don't have to change it unless you renamed the libraries that were the library names of that were generated as or were used for the Android dynamic link libraries. Then you have to change the system load library call. Another thing you need to do is to provide a juiceactivity.cs class, which is also an interop class for this Java class, so that the C# side of things can call this one. Okay, once we have coded all this stuff, then we still have to link it. So that's the last step. Linking is relatively simple and similar on iOS and Android, but with subtle differences still. On both platforms, you will need to include your binary libraries into the Xamarin project. For iOS, you can choose a directory structure as you please. For Android, you have to follow a prescribed directory structure. You can find out how to do this exactly in the sample code. For Android, then, you are done. But for iOS, you need to have yet another final step. You have to provide some extra settings on the project level, which are called mtouch arguments, which are basically GCC linker and compilation switches that tell Xamarin to link in extra iOS frameworks, for instance. For reference, these are the mtouch arguments. You don't have to memorize them right now. You can find them on the GitHub. Okay. I just showed you a game UI. It's also not much of a game, of course, but it's used a game framework to do the UI. But you can just as well use plain Xamarin, let's say, and to do a native-looking UI, and still consume that same JUCE library, of course. There's nothing that I've done has a dependency on CocosSharp itself. And finally, to wrap it up, so you might say, okay, I believe that you can do a test tone, and that you can have one rotary and one on-off switch. So what I could show you then as an answer to that is a little bit of a work in progress, which which tries to simulate, or not simulate, it actually does, produce a more typical audio workload. What this sample will do is it will show you that you can have a MIDI sequencer that plays MIDI in the background on the audio thread that can load sound phones, .sfz sound phones. And also it includes a little comping engine that I've been using. Can I have?
Yeah, you got 1 minute.
1 minute, okay. I'll just start it. Okay, it's not producing audio. Can we have a little bit higher volume, please? Okay, what you see here is a totally pointless UI, but it puts some more workload on it, and it uses a more real audio backend in the JUCE library. And the JUCE library is all doing all the audio heavy lifting, whereas the front end does only do the UI. You will see things like OpenGL drawings, particle systems, animations like zooming in of sprites and stuff like that. That was what I wanted to show you. I hope it can give you ideas. If you have any more questions, feel free to contact me, and I'll give you the links now for the GitHub. So GitHub source code is available at this URL. I've written some blog articles that explain all of this in more detail. Okay.